Hi everybody, this is again the MATLAB and Simulink Racing Lounge. Today, in today's session, we are going to talk about driver-in-the-loop simulations, and as you can see, we again have a co-host. We are preparing that episode with a team from Chalmers University. So first of all, let me introduce you to Håkan Richardson. Hello Håkan, nice to have you in the episode.
Hello Christoph, nice to meet you.
Perfect, so first of all, I'd like to give you an introduction of what are we going to talk about today. But before doing that, I'd like to ask you, Håkan, to introduce yourself briefly.
Yes, so my name is Håkan Richardson, and I'm an automotive engineering student here at Chalmers. Currently a member of the Chalmers Formula Student team, and have a background within Chalmers Vera team. So I'd like to talk about the topic of driver-in-the-loop simulations in regards to those two teams.
Okay, perfect. So thanks again for joining. So what are we going to do today? Well, you will introduce us to the Chalmers student racing teams. So what we've learned so far, there's not only a formal student team, but also a Vera team and participating in the Eco Marathon. Then we will properly introduce you to the technology behind driver-in-the-loop simulations. What we can say right now, it's more or less a driving simulator, but we will see the details afterwards. We will show you a software and a hardware demo. And last but not least, we will talk about the impact on your car development probably, and share some key takeaways.
Yes, indeed.
That's for that. Håkan, the stage is yours.
Thank you, Christoph. So I'd like to introduce the Chalmers Formula Student team briefly first. We run it as a one-year course here at Chalmers with students from all over the world. It's typically master students. And we've been building combustion engine cars since 2002. This year is the first year that we are building an official electric car. So we're very much looking forward to see how that car will look.
Okay, perfect. Just a question at that point. So we are doing the recording in February. Can you give some short statements about how far are you in manufacturing of your first electric car?
Yeah, the electric powertrain is slow in coming together. We're trying to prepare the last pieces so that we can get it into an engine test rig. And the remaining components, both carbon fiber and metal ones, are very much coming together. So we're looking forward to see the car be as a whole in a while.
Wow, sounds promising. Cool.
Yes, and as I mentioned before, the Chalmers Vera team, I worked with these guys during my bachelor years, and it's a team that competes in Eco Marathon. And the goal for those of you who don't know Eco Marathon is to travel as far as possible on 1 liter of gasoline, pretty much, or the energy equivalence of it. And as you can understand here, then minimizing the motion resistance and, of course, driver errors, those are two very important aspects to achieving this goal. So yeah, the Vera team competes here, and it's a good team, so the demands are high on the technology that goes into the car.
Well, allow me one question. You are the best example for that. Seems that the teams at Chalmers are closely cooperating. So are you sharing a common workshop, or are you all part of the same study course? So how is the interaction between the teams?
Yeah, the workshop is the same, and where the drivers are located, the base, are also in the same place.
Okay.
The technology exchange is not extreme since we're running quite different competitions, but the students, of course, we meet and we interact.
Okay.
Indeed.
Well, sounds great.
So this was also this team was the foundation upon which I did my bachelor thesis on, together with 4 other guys from Chalmers.
Okay.
And that's the driving simulator that I'd like to cover.
Cool. So let's jump to that one.
Yeah, exactly. It's kind of the core concept of driver-in-the-loop simulations, and especially this our design here. It's something we call the Stewart Platform Motion-Based Driving Simulator. And what it means is the Stewart Platform is the configuration in which we have the actuators that move, puts motion into the upper platform. And the driving simulator part is essentially having a driver within a simulation loop. So that's what we try to achieve here.
Okay, and we also see a rendering of a Stewart platform.
Yeah, exactly.
In the slide here. I think most of you guys have seen that or a similar concept of that before.
Yeah, exactly. It's typically the triangles that move that make out the platform. So you can use it as an engineering development tool, and that I think is the strong side of it. And we have chosen to use Simulink and MathWorks products as the software base, combined with a few other software interfaces that I'll talk about in a bit.
Okay, great.
You'll see throughout this that we have tried to keep using standard computer equipment. We're 5 guys in half a year. We wanted to ensure that we got something that worked, and then we utilized as much standard equipment that we possibly could.
That's again and again the key issue in Formula Student, or I guess also for other racing teams, limited resources, and that's why I keep it as simple and as standard as possible.
Yeah, that really helped us a lot.
Yeah.
So kind of the benefits that we hope to achieve with this, it's still in the implementation phase, but we hope to utilize it for driver practice. We're blessed with wonderful weather here in Sweden, so so getting a chance to actually test drive the car on the road is quite rare. So we use it for driver practice. But also, I mean, most of the engineering development today is done as computer models and CAD files. So you have everything you need in order to replicate the vehicle in a virtual environment. And that also is a good way to kind of test the equipment and in a serious manner.
No, makes perfect sense to me. Yep.
So the fuel efficiency, that's the primary goal for the Vera team here. And here you see the first half of what I consider to be the 2 halves that make out this experience that you get in our driver simulator. The first, I would say, is the visual and oral experience, saying images and audio. You have a 3D environment, which is very much like in any car game that you would use. And so you have this virtual 3D environment, and it's displayed around the driver to create the sense of immersion. And then you use standard hardware such as projectors, speakers, or monitors to kind of deliver this world to the driver and to create the perception of driving. But the second half is the physical experience. Here you have a platform which essentially tries to recreate the accelerations experienced in the real car. And the way you do that is by having the platform move based on the inputs that both the in-chassis movements, such as roll and pitch, but you also have world movements such as the lateral acceleration from cornering or these sensations that the driver experiences in the real car.
Okay, I consider that motion cueing as a technically quite interesting topic. So imagine you're braking with your car. How do you convert that into motions of the Stuart platform? It's static. Well, at least the chassis is static.
Yeah. So what we have done now is that the monitors are attached to where the driver sits. So you can lean the entire platform without the sense of the horizon moving in relation to your eyes. So what we do now is that we overdo the pitching movement of the car, and it gives you the sensation of being more thrown forwards. So it's still a quite rudimentary algorithm, but it's working.
Okay, but let's say the same strategies or the same theory is used in flight simulators or professional car simulators as well.
Exactly, and even more comprehensive ones.
Yeah. Okay. No, that's impressive.
So the visual stuff that I talked about before, kind of just a quick overview of how we did it. We started out with combining the Google Earth map from we're competing in Rotterdam in the Netherlands. Okay. So we put the track layout from the officials on Google Earth, and we tried to match the track to the actual world.
Okay. So you actually created a 3D model on your own. So you didn't have access to existing 3D models. You just created the one of the Eco Marathon.
Yeah, exactly. We used there a sort of a 2D foundation upon which we built and then we had videos from the track and pictures that we used also.
Cool. That's
so what you see on the right here is 3 renderings of the track. You can recognize on the middle one, the S corner that you see also below there. Okay. So it's that's what the driver sees. the hardware side, I thought of starting from the ground up, kind of going.
That's a good idea. Yeah.
The components that you see here. We have the cockpit is open now, so this would be the entry mode. And in the bottom here, you see the base. That is it's the heavy one that stays on the floor, and it's allows for stability in the structure. So on top of that, you attach 6 actuators, and then on top of that, you place the motion platform or the upper platform. To this, you then attach the chassis, which is a replication of the actual racecar. And then a rig that holds the 3 monitors around the car. So this is what we use to create the motion sheet. What you miss here is the control system that goes in the middle and bottom there.
Okay. As I'm completely new to the Echo Marathon, how is a person sitting in the chassis? Is it heads first or head first?
The feet are towards very close to the forward monitor, and then you very much lie down and look forward.
Got it.
So it's not a very convenient driving position, but it's good for aerodynamics.
Okay.
So we talked about the components that we have used, and we tried to stick to software and hardware that we knew would work. So we use standard computer equipment, standard actuators and power electronics, and also standard aluminum profiles and software that work well. Okay. So it's a combination of things that come together.
Okay. No, perfect. Makes a very good impression here.
So the software side is also necessary. It kind of becomes this dead piece of metal without a good software.
I think especially for that, software is key.
Yep. Yeah. So here is kind of a flow chart that describes the software that we've used. It looks kind of like a mess maybe to you now, but I'll go through it one by one, and I think it will provide an understanding of how it's built up.
I think the viewers of the Racing Lounge and also myself, we are used to a bit of complexity, so no worries about that. Let's go through that.
Yeah, we'll go through it.
Yep.
So essentially, in a car and in a driving simulator, especially, you have a very limited amount of input to the actual car, and you're limited to what the steering wheel does and what you do with throttle and brake, and all of that in our case goes on the steering wheel for the racecar. So we connect the typical, and again, the standard component PC gaming wheel to a PC by USB. And we send the input to a software from Cruden called Racer. Racer then packs this input into a network package and sends it to another PC via standard router and network to what we call the physics PC. And here's where you find the software from both MathWorks and from the other software from Cruden, where you essentially have the vehicle model interfaced with the Cruden software in and out. And from that we get essentially the speed and position of the car in the world.
Okay.
Send that back via the network to the master PC again, the orange one, and then we render a 3D environment on the monitors around the driver.
Okay. Allow me a quick question here. So what I'm seeing, at least 3 hardware platforms. So we have a master PC, a physics PC, and then an Arduino, I guess, for the motion controls of the Stuart platform. So is it a requirement to have 3 independent hardware systems, or why did you choose that configuration?
What this allows us for is to have the PC that does the rendering to be sort of suited for graphics power. And the physics PC to be suited for more computational power.
Okay.
And then we can also have the physics PC located further away from the sim and use it as a control station for the simulator.
Okay.
So and the Arduinos then are placed very much close to the motion platform. It's a convenient way of organizing it.
Okay, no, makes sense here.
From the vehicle model, at some point you will essentially calculate the lateral and longitudinal accelerations, and that's what we use as an input to the motion of the platform. So we have a PID regulator, standard one,
Yeah.
that sets desired speed of each actuator in order to achieve the position that we want it to have. And that is sent to the Arduinos via network.
Okay.
Standard router equipment again, and then we convert that in the Arduinos to PWM signals to the motion controllers, and then out to the actuators, the SKF ones that you saw in the pictures before.
Okay. So seems complex at the beginning, but if you explain it step by step, it's a very logic approach of doing that.
Yeah. So the actuators have these rotary encoders that we use to measure where we are with the actuators. So the Arduinos keep track of this, and then they report this to the Simulink model via the network again. Okay. So with that, we get a closed loop in the PID controller that we can use to make this whole loop go around.
Yeah.
And it's been a very convenient solution.
Yeah. Cool. Thank you for that introduction.
Yeah.
I think now we can move on into the software and the hardware itself a bit more.
Yeah, exactly. So on the software side, we can start off first with the hardware. Give you a little demonstration of how the hardware come together and how it works as a system.
Exactly, and how it actually looks like. What we have seen so far are renderings, and now we are really keen on seeing the driving simulator in work.
Yeah, indeed. So I'll have a little video for you.
Cool, great.
That I'll like to, and I'll give you some comments while it goes.
Perfect.
So what you see here is essentially what the driver sees inside the cockpit, and you approach the Z corner here, where you see the steering wheel. It doesn't move now since it's an AI driving it.
Yeah.
You see the buttons, and you see the interface that the driver would see on both monitors. And as this corner goes, so does the motion platform. So you see here the motion reaction of the platform. But the motion cueing for us, we can also just set a sine wave for the roll and pitch angle, and that's what we've done here for demonstrations.
Okay.
So you see how the platform moves, and you see it's based on a sine input.
Yep.
And we use universal joints in the upper platform here and below to create the 6 degrees of freedom that we want to achieve.
Okay. Cool. So it actually works. Great.
It does. We were surprised as well.
Yep.
So on the software side, this is powered by MathWorks and Simulink. So I'd like to just give you a quick overview first, and we'll jump into the Simulink model right after that. So this is how the Cruden software. Cruden is a simulator development company. And they have this interface towards Simulink that we have used.
Okay.
And you essentially have the vehicle model in the middle, and you have 2 blocks on the left side, 2 on the right side. The left ones are inputs, and the right ones are outputs.
Okay.
And the one closest to the vehicle model, the racer ones, are used for the graphics rendering. And the 2 outer ones are used for the motion of the platform.
Okay.
E2M is the motion platform. So
basically, what we are interested a bit, or I'm personally interested in the motion cueing and in the vehicle model. So if you could have a look at that in Simulink, that would be excellent.
Absolutely. I'll just give you a quick view of this. So this is the vehicle model. I thought we'd start there.
Yeah. Great.
And you have a very typical set of inputs to this vehicle model. You have throttle, you have brakes and reverse, starter, injector for the engine, and
Basically, what I'm seeing here is a big green block with engine and brake, and another white block with the bicycle model. So what is in that? So are you modeling the powertrain just in the green block and the vehicle dynamics in the white block, or how are you sharing the blocks here?
Yeah, that's correct. We're using the left one to model the vehicle behavior or the engine behavior, and we're from that we're deriving the vehicle longitudinal velocity.
Okay.
And that's the input to the bicycle or the single track model that we use.
Okay, so what we see behind the block called bicycle model is a single track model.
Yeah, indeed.
Okay, for example, guys, we have seen that before in the Racing Lounge episode that we've done together with AMZ Racing.
Yeah.
And they've based a lap time simulation on a 2-track model. Basically, it's 2 times a single track model. Great. I think that's well understandable for us here. Some further question on the engine and brake block. So how did you obtain the parameters? So how did you obtain your car behavior? Is it test results or are that underlying assumptions that you took?
Yeah, it's a combination of, I would say, both dyno test data of the engine, so that we know the characteristics of it, but also based on log data and the design parameters for the engine. Okay,
and how did you do the engine modeling, for example? Did you go the hard way via physical modeling, so modeling each component, battery, rotors, and all that stuff, or did you take more simplified models to keep that easy and lean?
No, we used a simple model for this this internal combustion engine that we use in the Vera car, and for a more comprehensive electric powertrain like the one we were going to use in Formula Student, we do more battery modeling and this aspect.
Okay, just a comment here. Battery modeling is also a nice keyword, pointing to another episode of the Racing Lounge where we've talked about battery modeling with a specialist of MathWorks sitting in the US.
Yeah.
But not so much advertisement here. I think let's move on.
Yeah, sure. Maybe you want to see the motion queuing.
Exactly.
Well.
This would be very interesting.
What you see here is a quite limited model. What we essentially do is that if I go back to the vehicle model here, you see here that we extract the longitudinal acceleration out of the powertrain model. And we extract the lateral acceleration out of the bicycle model.
Okay.
And then we output that to in this what we call G-forces.
Okay.
And that is the input that we use for controlling the motion behavior as of now.
Okay. And let's say all the movements of the Stuart platform are calculated then in the orange block.
Yeah, indeed.
Okay.
So we have
Sorry to interrupt. Is it stuff that you developed on your own? Made some assumptions. So if I'm braking, that means pitching of the entire chassis, or is it models and theory provided by Cruden in that case?
For the motion queuing, this is developed by us, and it's still a quite simple approximation of only using the G-forces to do this, and you use more advanced stuff to do it really properly.
Yeah.
But what we did here is that we tried to interface with the driver so that we can. You need to sort of wake up the platform, and you need to move slowly towards the middle position to where you can do the actual tilting of the platform. You need to ensure that you have the communication running, and so that doesn't spike and go away to a limit. And you also have a few. So you see the use start here or alerts is where we check. We get a signal back from the control system of how things are with the communication and temperatures and whatever we need to know. That's essentially how the motion queuing works.
Great. So this was a very nice insight to some special features or some details of your model. I guess the entire model is a lot bigger, but I think these were some really key parts. Thank you. Thank you very much for introducing us to that.
Yeah, no worries.
So I suggest let's move on and talk a bit about, well, the positive things, also about the problems that you experienced with that.
Yeah, sure.
Cool.
So for the result of this simulator, we actually managed to create a fully functioning driving simulator, as you saw in the video.
We have seen it, yeah.
Very satisfied with that. All 5 worked very hard, but it came together. It's really nice.
Great. And it seems that you've also won an award of the CDIO in that case. Impressive. Congratulations on that. Seems that you've actually done a very good job. But now, as we are engineers, we like to talk about improvement. So what is room for improvement of this driving simulator?
Yeah, so we kind of focused on like the reason why we won the award is most that we focus on both understanding how the user wants it and both the operate how the end user will use it in the future. And we concluded that we have three at least bullet points that we need to focus on in order to make this a really good product.
Yeah.
And that is tuning the vehicle model. We are currently using a single track one, as you saw before. We identified that we can actually approximate the vehicle good with a single track model since we're never traveling above 30 kilometers an hour.
Okay.
So the single track model in itself is a good approximation, but the tire models are very critical in order for this to be a good approximation.
Okay, so you already identified the problems in that, and well, there will be continued work on tire modeling, for example. Okay.
Yeah, exactly. The motion queuing algorithm is only based on the accelerations now, and here we want to look at other slip angles and also other criteria that are important for the driver to get really good experience.
No, makes perfect sense to me. And also, you well, what I read here, you plan to make the driver experience more realistic, right?
Yeah. And for everyone who has tried a simulator or you'll notice how critical it is that you don't have any other reference points than what you see on the monitors. So darkening the driver environment will really improve the experience of the drive. So working on that, and we're trying to hand it over to the Vera team in a good way so that they can actually utilize it in their development.
Okay. I had that experience in a driving simulator before, and really a dark environment without any reference to the real world. Well, I became seasick.
Yeah.
Because, but actually the behavior as such was very realistic. So totally agree that this is an important feature here.
Yeah, it is. So kind of want to jump to what we have future plans for the new possibilities for this driving simulator.
Yep.
Two systems first, and I'd like to discuss is the STM Discovery Board. Maybe you can take some more details on the Simulink hardware package.
Yeah, basically, there's no need to say so much about it, but the STM32 for Discovery Board is a hardware board, I would say suited for diverse purposes. So some teams use it for engine control or different control tasks. And the good thing about that board is that we have a Simulink hardware support package. And that means that you can send your Simulink algorithms or MATLAB scripts, MATLAB functions directly to the board. So the code generation is not far away. You just can push your models onto that board, and they are compiled automatically. I think this is the big strength of that board in combination with the Simulink.
Yeah, so we actually managed to get this specific board to power the combustion engine that is in the Vera team car.
Okay,
that is
very good example.
World of opportunities for us for other system. But as many other teams do as well, you do some kind of driver environment mock-up where you test angles and steering wheel positions. But what you don't consider when you do this is the actual, you do a static mock-up.
Exactly, it's pretty static.
Yeah. So with the new simulator that is coming to Chalmers, you see it's a Cruden simulator. You see it below. You can actually do, let's say, a driver testing mock-up where you make this into a dynamic test. You drive the Hockenheim or the Silverstone track in the simulator in the driver mock-up and see how different steering wheel positions affect the driver performance.
Exactly. You can see what the driver is doing, how he's moving, where he is looking.
Exactly.
What is required to be fast on the track. Well, that's impressive to move the mock-up and development or the drive environment development from static to dynamic and real-world behavior.
Yeah, and this goes for many other systems that are commonly described in powertrain and vehicle dynamics courses.
Yeah.
So it's a whole world of opportunities that is opening up with this kind of system, and we're hoping that the two simulators will work well in conjunction for the team courses.
Well, and the good thing is for you as a university, it's not restricted to Formula Student or Eco Marathon. As you said, it's multi-purpose here. That's very impressive. That's cool.
Yeah, and with the power of the eFiceNet Simulink interface that you saw before, then we can really use we can have a model of a system in Simulink and actually test it sharp with the driver. So it's a really cool opportunity that we hope to use.
Great. So I wish you all the best, a lot of success with that approach.
Yeah.
I think now it's time to get to move on to the key takeaways of today's episode.
Yeah, indeed.
Well, why not? Usually I do that, but I think today you can go through them and explain a bit why you choose them and why these are the most important ones.
Yeah. So the first one kind of goes back to the design of the complex system that is the driving simulator. So when designing a complex system, use solutions that work well and spend time on the interfaces. For us, typical interfaces were the software interfaces between communication between the different devices, and also integrating the hardware movements and how fast they are to the actual software. It's usually the interface that takes the most amount of time, and they are underappreciated that way.
Yeah. No, totally agree. Second one, engineer systems so that the user can fully utilize them. Well, I think that phrase stands for itself. Totally agree. Just create stuff that is useful. Don't waste your time. Don't waste your time on stuff that you never use again.
Exactly.
Any amendments to that, or any examples from your work experience?
Yeah, I mean, this is very much the foundation upon which we won the award for it. That we designed it with the end user in mind, and that they can actually use it for their development. So it's not just for engineers, but it's for the user of it.
Okay, and that statement nicely links to the third key takeaway. Get the most important person in a race involved early. Get the driver involved early.
Exactly.
Makes perfect sense to me.
Yeah.
Great. Håkan, thank you very much. We have seen another impressive approach, a multidisciplinary approach, not just involving Formula Student, but other teams. It was a rather special session. Thanks a lot.
Thank you.
It was a pleasure to have that talk with you.
Thanks to you too as well.
Perfect. And for the frequent viewers of the Racing Lounge, let me go to the last slide.
Yeah.
Or let Håkan go to the last slide. Thank you. For further reference, just visit our mathworks.com/racinglounge. There you can find all episodes that we've published so far. If you want further information of our MathWorks support for Formula Student, go to the respective Formula Student webpage. And as usual, we are very keen on receiving your feedback. So in case you liked that session, in case you have further ideas or comments, mail us using formulastudent@mathworks.com. And if you do use our software provided by the Formula Student software offer, we would be really keen on if you use our logo on your car and your reports. So thanks again. Thanks for watching, and see you next time.
Thanks.